All right, and we're back at 3-4, fourth section in the third chapter, with the section being over systems of nonlinear equations, and specifically we're going to do graphing. At some point we will solve algebraically, but that will probably be in the next chapter. So just one learning target, I can solve systems of nonlinear equations by graphing. So before we begin, we're going to do a little bit flashback to the past, specifically, actually, the very first section that we did in this class. So luckily, I have all of our notes from every lesson here. So I'm just going to go ahead and just pop this under the dot cam real quick. And so what I'm looking at here is us solving systems of linear equations. Now notice that today we're going to be using parabolas. So they will not necessarily be straight lines. Some will be, but most of them will not be. And when we graph, so just take a look over this and think to yourself, what were we doing? What was the object of our problem, or of like what was our end goal to do to be able to figure out that the system that makes both of these true was the ordered pair x is 2, y is 3. So if you're kind of looking over this, it does kind of look like we kind of labeled one as a black line and one as a red line. And then we did a little bit of work to graph, but we just graphed the black line, graphed the red line, and our answer was just where they intersected. Okay, so that was how you can solve systems of equations, linear or nonlinear, using the graphing method. So we're actually going to do the exact same thing today. The only difference is we'll be dealing with straight lines and curves, as opposed to the previous time we used this topic, it was strictly only straight lines. So that's really the only extra curveball that we're being thrown to. Okay, so right here I have a little table that will kind of outline the different types of answers that you can get. Because before, if you recall, we could get one solution, which is where the lines would cross one spot right in the middle. We would get no solutions, which means the lines were parallel. And then we would get infinitely many solutions. That's when the lines would overlap each other perfectly. So today, we're going to have similar situations, though there's going to be one extra. You can still have all of those same options, but we're gonna take a look and see how it might be a little different. Okay, so if I have one linear straight line and one quadratic parabola, we can get no solutions. An example of that would be, let's say we have a parabola, and let's say it's opening up. So we just have a parabola like this. Somewhere on our graph, it doesn't really matter where on our graph, just somewhere on our graph. So no solutions, to me, would indicate that our curve parabola and our line are not touching at all. So we just have to draw some line somehow that just kind of cuts right underneath of it, never ever hits any part of this line here. So an example of that could be just maybe like a straight line like this. Okay, it doesn't exactly have to be one opening up and a line underneath. It could be opening down. There's a lot of different things, but moral of the story is essentially, our line is just not going to touch our parabola. That's what the situation is going to be when I have no solutions. Okay, what if I have two quadratics? Now, this is possible to have two quadratics. There's a bunch of different ways. So, again, let's say I have a parabola, and let's just say this one's opening downward. Okay, so there's a bunch of different ways. We could have one that opens wider and goes right over top of it, or, kind of a little more realistic sounding situation would be, we have a parabola that opens up like this. They just will never cross. So even though we have two quadratic, that concept of those those curves never touching each other is the same. Like, they're just not going to touch each other. Therefore, there's no x and y pair that's going to make the red and the black curve true at the same time. Okay, one solution, as you may have kind of already come to the understanding from the very first section that we did, is one solution is just when those functions, graphs, touch each other exactly one time. Now, it's a little bit tricky with the curve in the line. So again, let's say I have the same situation where I have a curve and it's like this. There's my parabola. The situation where it hits one time is the line is going to come in at just such a perfect right angle here that it runs, and this is actually what we would call tangent to it. You may have heard a little bit of tangent lines in geometry when we talk about tangent lines to a circle. It just hits that circle one time. The concept is the same here. It's tangent to that curve, so it's just going to touch it exactly one point, and then it's done after that. So that's kind of what it would look like, right? It just hits each other one time. Okay, two quadratics. Okay, two quadratics, again, if we have one opening downward, like this, we could, honestly, you could just have their vertices touching, right? So it almost looks like a hourglass, okay, where they just hit exactly one time. I do think there's a possibility that the curves just hit each other exactly once, like maybe here and here on the edge. I would have to look into that some more. But essentially, again, concept is they hit exactly one time. That's how many solutions we're going to have. Okay, two solutions. Two solutions would be it hits the graph twice. So we've got to think, how is this line going to hit this graph twice? Well, if I were just to take this previous one, take this red line, just move it up, it's going to cross here and here. And that's what's going to essentially happen. So if we have a parabola opening upward like this, and then a line cutting through it at some angle, doesn't really particularly matter, but they're going to hit in two spots, right here and right here. And those two XY pairs would make the both the red and the black line true. So this particular one has two sets of ordered pairs. So that would make it true. Okay, parabolas. Okay, this could be very, very similar, right? It's just going to hit each other two times. So let's say we have a parabola like this, black one opening downward. Well, we could have a parabola that maybe goes something like this, right? A little bit wider than all the other ones, that's fine. But, you know, they hit in two spots. And those two spots are going to be where our solutions lie. So that's just kind of visually the different types of things we're looking to. I think this will come relatively natural to us because based on the very first section that we did in this whole year, it's pretty consistent with that. And that is strictly reviewed. That's graphing systems of linear equations was, you know, maybe something you started in the 8th grade. So now we're just developing onto that. The only difference is we're using curves. So the only thing that I would say really can make this particular section difficult is when we are graphing. We have three different ways to graph our parabolas, and all three of them have like bits of given information. I actually made a little video kind of outlining this, and then looks like I forgot that I actually put it on our notes, which I'm glad I did because it makes it a whole lot easier. So let's just kind of go through. So standard form here, I'm going to highlight this because this is our standard form. Okay, y is equal to ax squared plus bx plus c. Okay, and from that information, you get some freebie things that are going to help get you started, right? The first is that the easiest thing that you can get from this is the y-intercept is always the ordered pair 0, comma, whatever c is. You can find the axis of symmetry by using x is equal to the opposite of your b value divided by 2 times your a value. You know, just a formula and go. And then whatever that x value is, plug it into the function for the y value. Those two together, okay, is your vertice or your vertex. Okay, so if you remember standard form / polynomial form here, this one's actually kind of the hardest one to graph, although it has some really nice features to it. Vertex form, y is equal to a times the quantity of x minus h squared plus k. Vertice, really easy, h comma k. You do have to remember, though, that when I have x minus 2, h is positive 2 in that situation. But if I had x plus 2, h would be negative 2 in that situation. We'll talk about that more. And then your axis of symmetry is just simply x is equal to h. And then from there, you can get started, right? All these problems kind of feed off of each other. You just have to be able to get started. And then lastly, we have intercept form, which is y is equal to a times the quantity of x minus p times the quantity of x minus q, where p and q are your x-intercepts, okay? And then your axis of symmetry is technically p value plus q divided by 2. If you recall from that section, which is 3, 2, I just simply said find the line that's in between our two x or x-intercepts. And then you can use that AOS stands for axis of symmetry, number to solve for y, same that you would do here. Okay, so these are our 3 basic forms. All of this stuff is things that you're going to need to know how to do. In fact, I would say that you should actually already know all 3 of these. And if you do know all 3 of these, this section is going to be absolutely no problem. But again, it's quite a bit of information, but you do absolutely need to know all of these parts for all 3 of these forms. Okay, so let's actually go ahead and get started. Okay, so I want to solve this system by graphing, and I'm going to graph by hand, okay? So what we need to do is we're just need to graph the first one, then graph the second one, see where they intersect, okay? It's as simple as that, so let's go ahead and get started. I'm going to call this one here the black line, okay? And as I'm looking at this, I need to start identifying what form it's in, and then once I identify what form it's in, get started and have it graphed. Okay, so to me, I'm looking at it, I have like 2 groups of parentheses. This very, very much aligns with our intercept form, right? Y is equal to A times that and that. Just in this situation, our A value happens to be 1, so that actually kind of makes it easier. Okay, so if you look at that, that means we know for the black line, we have x-intercepts. Okay, what are our x-intercepts? Our x-intercepts are, okay, so here it would be -2, right? Because x minus p, so that means p would have to be -2 in this situation to turn this into x plus 2. So we have 2 x-intercepts. So we have the first one being -2 and the second one being +3. Okay, so I can just go ahead and graph that. -2, 1, 2, +3, 1, 2, 3. Okay. So we have to figure out where the axis of symmetry is from here. So so as I'm looking at this, it's like 1, 2, 3, 4. There's like 5 spaces. So we actually know it's kind of, it's going to be 2.5 in. So I'm not 100% sure where that's at, which will happen on occasion. Okay, so if you're not 100% sure where that's at, what you can do is on your sheet, it does have a formula. Axis of symmetry is p plus q over 2. This is the average of the 2 numbers. So we're going to find the axis of symmetry, which is going to be -2 plus 3, all divided by 2. -2 plus 3 is 1 over 2. So it just looks like it's x is equal to 1/2. So I'm going to do my best to graph that. It's not going to be perfect, but it should be exactly halfway in between 0 and 1. So we're just going to go ahead and do our best. We do know that when you graph by hand, essentially it is just a sketch, although we want to try to be as accurate as I can. So this is x is equal to 1/2. Okay, so what do I do from here? Well, I need the vertex, right? And I do expect the vertex to be below these 2 spots here. And the reason I'm expecting that is because my A value is a +1, so I know it's going to open upward. It's going to be something like this. So if I want to find the axis of symmetry, what I need to do is go ahead and plug in 1/2 into this function. So I need to find the vertex. And the vertex is just going to be y is equal to, okay, this one's going to be 1/2 for x plus 2, and then 1/2 for y minus 3. Okay, so y is equal to, well, 1/2 plus 2 is 2.5, and 1/2 minus 3 is -2.5. And then those numbers multiplied by itself, not 100% sure what that is off the top of my head. Is -6.25. Okay, and we are getting some decimals. Totally fine. So -6.25. So -1, 2, 3, 4, 5, 6. And then 1/4 is going to be 1/4 of the way through here. So I think right here looks like a very reasonable spot. Again, it's not perfect, but we have a pretty good understanding. Plus, we have the algebra to kind of back up that that's what that ordered pair is. Okay, Next thing we have to do is we just have to find some other points, right? So we need to find any ordered pair. So I don't think it's unreasonable for us to do either 0, which is a half a unit away, or like -1 or 2. I'm actually going to pick -1 here. I'm going to pick x is -1. I'm going to plug that in. Okay, so here I'm going to pick x is equal to -1. And then I'm basically going to do the exact same thing I did for the vertice, or for the vertex. But instead of a half, I'm picking -1. Okay. So y is equal to, this is 1. And this is -4. So that means this is -4. So now I have the order pair -1, -4. Whoops, didn't mean to have that sideways. -1, -1, 2, 3, 4. 1.5 to the line, half and 1 away from the line. Okay. So that's just kind of the basics start of this. What I'm actually going to do now is I'm going to go ahead and I'm going to do the next one here. I'm going to get started on it because it's very possible I might need to find some more ordered pairs than the 5 I have here just to make sure that they match well. But for the time being, here's my curve. Okay. Okay, so there's my curve for the time being. And now I'm going to do the next one, and this one we will do in red. Okay, so here we know that this is, as I look at this, it looks like it's in vertex form. So vertex form, okay, is kind of the easiest. You just find h and k, and then that will be your vertex. Okay, so here I want to find my vertex first. And that's h comma k, which is -3 comma 6. -3, 1, 2, 3, comma 6. 1, 2, 3, 4, 5, 6. Okay, and then my axis of symmetry is right on this line. Okay, which is x is equal to -3. Okay. It looks like I didn't get that line perfectly, but that's okay. So now, as I'm looking at this, it helps to know different things about the a, h, and k value. For example, I know this is going to open downward, and it's going to be kind of wide. Okay, so it seems realistic for me to maybe hit it here. It also seems realistic that I'm going to hit it maybe, or I'm going to hit the next curve like somewhere up in here. So we're going to have to see, and we might have to do more for the black line. Okay, so let's go ahead and find when x is, let's just go ahead and do when x is -2. Okay, we'll pick x is -2. Okay, we're just kind of working towards the line, or towards the other curve. So when x is -2, okay, we get -1/6 times -2 plus 3 squared plus 6. So this is a 1/6 of 1 squared plus 6, which this is just 1 squared is 1 times -6. So this is -1/6 plus 6, which is equal to, that's 5 and 5/6. Like 5.83 repeated. Okay, so this isn't going to be a great one to graph, but this is okay. So when I pick -2, it's like 5.8 something. So it's like right here. So I know that these x values don't match up. Okay, so that's kind of telling me that I probably want to take this black line and I want to check when x is -3 because there's a chance that it crosses right here. We'll have to see here in a minute. We'll go back. Okay. But if you recall from when I taught how to do these, when I said whenever you have a fraction here, it helps to do like units 6 away from the line, right? We're almost guaranteed a whole number when we're there. So what's an x value 6 away? 1, 2, 3, 4, 5, 6. It looks like x is 3. So here I'm going to pick x is +3. Okay, so when x is positive 3, we get y is equal to negative 1/6, and then x is 3 here. Okay, so then 3 plus 3, well, let's just throw this in the calculator so I don't have to use so much work on here. So here we're going to go negative 1/6 times 3 plus 3 squared plus 6, which is 0. Okay, this is actually great, right? Because now we have this ordered pair 3, 0. So we see that they overlap exactly on this spot. So 1, 2, 3, 4, 5, 6 to my line. 1, 2, 3, 4, 5, 6 away from my line. So right here. Okay, so here I kind of have a curve, and you know it's going out like this. Okay, we do technically have 5 points based on what I have, so that's good enough for the red line, but we don't have, it's pretty clear that we're going to have 2 intersecting spots, right? This black line has to intersect this red line at some point, but we only have one of the intersecting spots, so let's go ahead and pick x as the negative 3 and see if we can get a little closer to figuring out where the black line does, or intersects. So if I can get my black pen out, okay. I'm just going to do the work down here. I seem to have enough space. So here for the black line, I'm going to pick x is negative 3. And I'm going to go ahead and check that out. So that means y is equal to negative 3 plus 2 times negative 3 minus 3. Okay, let's go ahead and just throw that in the calculator. Okay, negative 3 plus 2 times negative 3 minus 3 is just 6. Okay, so this is y is equal to 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. This is perfect, right? Now they intersect there. 1, 2, 3 and a half to the line. A half, 1 and a half, 2 and a half, 3 and a half away from the line. Okay, so then let's go ahead and extend our graph out a bit for our black line. Okay. So we know we have 2 points of intersection, which is great. Okay, we see that it intersects here and here. Okay, those are our ordered pairs that are going to make each of these true. So that means I have 2 answers. The first one looks to be 1, 2, 3, 0. And the other one appears to be negative 3, 6. Okay, now this next part that I'm going to do is not required, but I just want you to truly see what it means for these points to be solutions. So what I'm going to do is I'm going to go ahead and pick each of these functions, and I'm going to plug both of these in using the calculator, and you're going to see that when I plug in my x value, both equations are going to give me the same y value. So I'm going to do the black one first. So here I have 3 plus 2 times 3 minus 3. Okay, and that is 0. So when I plug in 3 into the top one, I get 0 out. So what it means to be a solution is when I plug in this x value here, 3, into the bottom equation, it should give me the exact same value. So let's go, or it should give me y value of 0 as well. So negative 1/6 times 3 plus 3 squared plus 6, it's 0. Okay, so this one go ahead and checks out. Okay, and then the next one, when I plug in negative 3 into both equations, I should get positive 6 out. So let's go ahead and see that. So negative 3 plus 2 times negative 3 minus 3. Oh my goodness, hitting all the wrong buttons today. And that's 6, so that works out. Let's go ahead and do it for the other function here. Okay, and it's also 6. So they both check out. Okay, so although that's not required, I mean, using the calculator to check your work is very, very minimal effort. I would really highly recommend you doing it, okay? So those are our 2 answers. Here's one thing that can be kind of inconvenient is that you might have, like normally I just say if you're 5 points, you're good. In some situations, you might have to just continue until you're out of space on the graph to see where they're going to intersect, which isn't the end of the world, but you know, it is a little bit of extra work, but if that's the worst thing that's happening to you today, you're having a pretty good day, I would like to think. Okay, so let's go ahead and move on to 2. So notice that in this one here, I went back over how to graph intercept form. And I went back over how to graph vertex form. So the next example I'm going to have for you before I let you all start is I am going to do one that has a straight line and one that has a parabola as well. And we're just going to see how many solutions we have, if any, and then we're going to mark them. Okay, so here, this top one here is in slope-intercept form. So here I'll call this the black line. Okay, and as I'm looking at it, it is in slope-intercept form, y equals mx plus b. So I need to find my m value and my b value. Okay. B value is clearly -2, but what's my m value if there's no number being multiplied by x? So hopefully you're mulling it over a little bit and you think to yourself, well, 1, which means I have a rise of 1 and a run of 1 as well. Okay, so let's go ahead and graph this line. So I'm going to start at y value of -2. Slope-intercept tells you find the y-intercept of -2, which is right here, and then a slope of 1. +1 on the top tells you up, and +1 on the bottom tells you right. So I'm going to go up 1, right 1. Okay, so I'm just going to go ahead and fill out about basically all of them, if I'm going to be honest. I kind of like filling them all out. Get a little OCD going on today, no big deal. Okay. Okay, and so then I get to connect all of these dots. This is the real reason why I like filling out all the dots, is because when I connect them, it's real easy when they all have a dot on it. So, and I'm just a little bit OCD again. Okay, so let's go ahead and do the bottom one. Bottom one will be done in red. Okay, so this is in red. It's in standard form. So when I take my sheet here and I look at standard form, really the only information you get is the y-intercept. The rest you kind of have to work for. So let's just go ahead and we'll start with the axis of symmetry to get the vertex. Okay, so here I want to start with the axis of symmetry, AOS, which is x is equal to the opposite of b. So what's the opposite of my b value? Other words, what's the opposite of -6? What's +6? Over 2 times a. Well, what value is my a value if there's no number written there? Again, it's 1. So here we get 6 over 2, which is equal to 3. So my axis of symmetry is the line x is equal to 3. So let's find 3. 1, 2, 3. Okay, and I know my vertex is going to land on that line here. I got to pull this a little closer to me here. The vertex is going to be somewhere on this dashed line, which is my symmetric x is equal to 3 line. Okay, how do I find the vertex? Well, once you find the x value for the axis of symmetry, just like the previous one, once you have your axis of symmetry number, you plug it in to find the vertex. Once you have the axis of symmetry x value, you plug it in to find the vertex. So here I'm going to find my vertex, and it is going to be y is equal to, all right, and then here I'm going to have 3 squared minus 6 times 3 plus 8. Okay, so 3 squared is 9. -6 times 3 is -18. Plus 8. Okay, so here, these two together is -10, and then -1. I believe this is -1. I'm going to take the calculator and just check, because I want my graph to be correct, so I don't have to go back and redo it. Okay, perfect. So here the ordered pair is 3, -1. So 1, 2, 3, -1. Okay, so there's my vertex. So another thing you can be thinking about is like, okay, am I going to have solutions? Because if this opens downward, okay, there's a very real chance that we're going to have no solutions, right? Because if it opens here and just goes like this, we might not ever cross this line. But our A value is a positive 1, so that means it's going to open upward, meaning we definitively are going to have two solutions here. Okay, so let's go ahead and find our freebie point. Our freebie point is 0, comma C. 0, comma whatever my C value is, that's the y-intercept. So here I'm going to get my y-intercept, which is going to be 0, comma 8. 0, comma 8. So 1, 2, 3, 4, 5, 6, 7, 8. Reflect across 1, 2, 3 to my line, 1, 2, 3 away from my line. Okay, so unfortunately that did not get me any points of intersection, so I'm going to have to go back through and I'm going to have to probably work for 2 and 1, unfortunately, but I think we'll be fine. Okay, so let's go ahead and pick when x is equal to, let's just do 2. Horizontal lines here maybe to kind of separate these out. So when x is 2, that means y is equal to 2 squared minus 6 times 2. Okay, and then plus 8. So y is equal to 2 squared is 4. Negative 6 times 2 is negative 12. And then 8. Okay, so 4 and 8 add to 12. Negative 12 and positive 12 are going to cancel out to 0. So now I have the ordered pair 2, comma 0, which is right here. So there's our first intersection point. Okay, so we already know this is going to be 1, 2, 0. Okay, there's my first intersection point. Let's go ahead and find the other one. Let's go ahead and pick when x is 1. Okay, so that means y is equal to 1 squared minus 6 times 1 plus 8. Y is equal to 1 squared is 1. Negative 6 times 1 is negative 6 plus 8. These add to 9, and then 9 minus 6 is 3. Okay, and then this work here could be done in the calculator if you desired, which I don't care whether you do or you don't. Okay, so then this is 1, 3. 1, 2, 3, and then reflected across. 1, 2, 1, 2. Okay, there's my second one right here. Okay, so let's go ahead and connect this curve the best we can. Going through all of our ordered pairs that I know it goes through. Okay, I did a pretty good job there, actually. That's a pretty good parabola. I'm going to brag about that. That's a good one. Okay, so we get 2 ordered pairs right here and right here. Okay, here's the first one. It's 2, 0. Okay, which is this one. The next one appears to be 1, 2, 3, 4, 5. 5, 1, 2, 3, 5, 3. Okay, and again, if you wanted to, you could plug this into the calculator or into the function by hand to validate that this will prove each of these to be true, but these are our answers, so we are going to be good to go with that. All right, so this one also had 2 solutions. Okay, so what I want you all to do is I want you to move on to the next page. It has actually 2 examples for you to work through, and I'd like you to work through both of them, okay, and then check your work with mine. Notice, I went through all 4 of the different things you're going to be expected to graph. Parabola in intercept form, parabola in vertex form, straight line parabola in standard form. Okay, now the straight line and the standard form one won't always be together. The intercept and vertex form won't always be together. They'll be mixed and mashed together in a variety of ways. I'm going to ask that you are able to just look at the problem and know how it's going to be done. Okay, so right now is a great time to pause the video and check your work with mine when you are done here in a moment. Okay, so I went ahead and did the problem kind of in the background so we wouldn't have to walk through every single little bit of it, but that I already have it written down here so I can kind of go through it a little bit quicker for you all. So as I'm looking at this, I have a black line and a red line. The black line has a slope of -2, which is the same as -2/1, which means down 2, right 1. Negative on the top tells me down. +1 on the bottom tells me right, with a y-intercept of 3. So I start at 3, and I go down 2, right 1, over and over and over. The opposite of down 2, right 1 would obviously be up 2, left 1. Okay, so I fill out the graph like that. Okay, for the red curve, okay, I know that it's going to open down because I have an a value of -1, but it's in intercept form. So I find the two intercepts, -2 and +4. Okay, -2 and +4. Remember, the basic formula calls for subtraction here, so it's always the opposite of what it appears to be. -2, +4. Okay, the axis of symmetry of -2 and +4 is exactly in between, which is at +1. If you decided to use the formula, it's -2 + 4 divided by 2, which is 1. Once I have my axis of symmetry number, I plug it into the function for the x value. So I replace all x's with 1s. Okay, so 1 + 2 is 3. 1 - 4 is -3, so 3 times -3 is -9. But we have to take the opposite of it here, so opposite of -9 is 9. Okay, next I just start plugging in x values and getting out y values. Now, since the graph starts so high up, I decided it might be a good idea to do multiple points. So again, on these problems, you're probably going to end up having to do more than the normally required 5 points. Here I ended up with 2, 4, 6, 8, 9. I ended up with 9 on this one, just on the red one here. So sometimes that's going to be required of you to do. Okay, so after I plugged in all of these ones here, I found that it intersects at 2 points here and here. Okay, so those are my two ordered pairs, and I checked them with the calculator, and they do indeed work. I'll leave that up for one more moment in case you need to pause the video and see everything. Okay, next, for letter B, okay, this one here was a little bit different. It was two curves. Okay, and the first one in black I identified in standard form, so I need to start with the axis of symmetry. Opposite of b over 2a, which is -1. So I drew an axis of symmetry of x equals -1 here on the black dashed line. Next, I plugged in x is equal to -1 in for x to find the vertex, which starts at 0. Okay, from that point on, I went and picked x values. I just picked random x values until the graph was filled out completely. So I get the ordered pair 1, 4 and 2, 9. Okay, so 1, 4 reflects here, and 2, 9 reflects here. Okay, then I did the red line. Okay, the red line here is in vertex form. Okay, so 2, -3 is my first is my vertex. So I drew the axis of symmetry here. X is equal to 2. Then again, I picked x values until I filled out the graph. So x is 1, x is 0, and x is -1, with a y value -2, y value 1, y value 6. Okay, so -2, and then reflect here, 1 reflect here, 6 reflect here. Okay, so here I'm seeing that it already crosses here, but I'm not really seeing any other spot it crosses. Okay, now, so it's 0, 1 is where it crosses here. Is x is 0, y is 1. They both hit here. Now, the only thing that we don't know is, like, how do I know, like, it doesn't extend out and doesn't cross, like, somewhere up here off of the graph? Or over here off of the graph? Well, the main reason I know that it's only crossed once and it hasn't crossed again since is that the a values are the same. So after a certain while, since this one's lower, okay, from this point to this point increases at the same rate from this point to this point. And so every point here, it will increase faster and faster, but so will this one. So once they've crossed once, Since the a values are the same, they're not going to cross again. They have just definitively crossed one time and one time only. So this is another way we can see graphs cross exactly one time. So this one, we're just going to have one solution. Okay. Let's move on. All right. Okay, so this is more of a word problem. And when we do word problems, okay, I'm going to suggest to you to use the calculator, mostly because a lot of times they're not going to cross at a nice, neat point. They're going to cross at like maybe 7.35, $7.35 or something along those lines. And so we're going to use the calculator to solve for most of this. Okay, so let's just dive on into it. The revenue for school play is given by the function. R is equal to negative 50 t squared plus 300t, where t is the ticket price in dollars. And we talked about last time how the relationship between the money and the ticket price actually does form a parabola, because it's going to be higher at some points, but once it's so expensive, you're not going to be making any money because you're going to be scaring people away, as opposed to where it's so low, you're not having the price be high enough for it to actually make any money. The cost to produce the play, though, is a linear function. C is equal to 600 minus 50t. Okay, so determine the ticket price that will allow the script in the queue to break even. Essentially saying, I want to know when the revenue is equal to the cost. Essentially telling me when I'm breaking even. Okay, so this one here, even though I have an R and a C, they're both talking about dollars just completely in general. So we can both kind of treat them as Y, right? The revenue and costs are still talking about dollars in the same increments and amount. So we can go ahead and just, we can treat them both as Y. So literally most of the work's done on the calculator here, okay? So the first thing I'm going to do is I'm going to hit Y equals. Okay, and I'm going to clear out this top function. And what I'm going to do instead is I'm going to write the top one R here. So negative 50. And again, there's no t value in our function. It only reads x's and y's. But t can functionally be worked as x. So we're just going to use x. Again, x is this button right here, right next to the alpha. Okay, x squared plus 300x. And then the next one is 600 minus 50x. Okay, if you're getting an error, okay, I can almost guarantee one of two situations is happening. The first is that this, what I have highlighted on the calculator, you use subtraction symbol instead of negative number. Okay, so this one needs to be negative number. We're not subtracting it from anything. It's just a negative 50x squared. Okay, that's the first thing. The second thing that could be throwing it off is if you go ahead and hit second y equals, this first plot might be on. So go ahead and turn that plot off. Whoops. So second y equals. Go into that plot and highlight and turn it off. Okay. More times than not, almost every problem I've ever had with the calculators when we're doing this comes down to one of those two things. Okay, so if you're getting something else like syntax, means you typed something wrong in here. But those are always one of the two issues 9 times out of 10. Okay, so let's go ahead and hit graph. Okay, so as we're looking at this, my window is all messed up. But this is from the word problems that we did in 3.3. So we are probably not looking anywhere close to where we need to be. Okay, so let's just go ahead and... So negative 50. So this graph here, where is this glare coming from? All of a sudden, it was so perfect. Okay, so this graph here starts at 600 and then decreases 50 every time. So it seems reasonable to maybe have my Y max be at like 1,000, because that one starts at 600. Where the Y minimum, honestly, we're not interested in anything in the negatives, so let's just have it at 0. Okay, the x's, I really have no idea what it's going to go down to. But again, I'm not really interested in negative x values, so we're going to start it at 0. And just to be safe, let's go all the way to 50. Okay, so hopefully you followed that pattern that I knew that this graph is going to start at 600 and move down 50 every unit. So hopefully you'll recognize that pattern of just like how I'm using the numbers in the functions to give myself something reasonable to start with. Okay, then go ahead and just hit graph. Okay, so it looks like I definitely picked too many x values. I went all the way to 50. Okay, so if this is 50 and this is 25 in the middle, I think we can go down to that 20 might have been right. So let's go ahead and pick 20. And I'm even going to take a little off the top here just so we can get a little better picture. Way better picture. Okay. Now, the only problem is I'm having here is that I really honestly don't know if it's hitting that line twice or once. So let's try to zoom in again some more. So this was 20. Let's go all the way to x is 10. And let's cut some more off of that. Let's cut some more off of that x and that y value. And so this just allows us to zoom in more and more and kind of see better. See, so it does cross twice. So that's important to know. That at two different points it's going to be equal to each other. Okay, so it looks like I'm just going to sketch this graph here just so we have a little better understanding that if I need to mark something up. So it looks like we have something like this and then something very slight like this. Okay. All right, so let's go ahead and actually solve this problem. So I want to know when this cost, okay, matches this revenue. Okay, I want to know when they're the same. So my revenue, okay, so what I'm going to do is you're going to go ahead and you're going to hit second and then trace. And we're looking at the same things, but what are we looking for now, right? We're not looking for a random y value. We're not looking for where it crosses the x-axis. We're not looking for the vertex at all. We're looking for where two curves are going to intersect. So we're going to hit intersect. Okay, so the first curve, what I want to do is I want to get to the first spot where I think it's crossing as close as I can. So let's say like right here. Sure. And then the second curve, I want to be close to it. And then guess. Okay, and so it says at 450. Okay, and so then the next is going to be the same exact thing, but the only thing that's different is I want to get over to this curve more or less. Okay, there we go. So you have to enter 3 times, and this is 400. Okay, so we know it crosses at 450, and then at 400. Okay, so the question asks, determine the ticket price that will allow them to break even. So if I have them go $3, I'm going to break even. If I'm $4, I'm going to break even. Okay, so those are the two different ticket values. Okay, at $3 and $4, they'll break even. Okay, I'm going to add one little extra wrinkle. What do you think they should be charging so that they actually make a profit, right? So that means our revenue, amount of money revenue, is going to be higher than our cost, right? So which R is this one here, is the curve, and the cost is this one here. So somewhere in between $2 and $3, right? Somewhere on this curve is where my revenue is higher than my cost. So really anything in between $3 and $4 ticket prices is going to be positively impacting me to make a profit, right? So if we want to pick any amount of money, like if we want to pick down, like for example, if we pick $2, let's say it's right here, our cost is so much higher than our revenue. We're not making any profit, right? Because if we take our cost, let's say this is $500 and this is our revenue, this is $200. We're making $200, but we're spending $500 on the play. Okay, as opposed to here, we're breaking even. Here, we're breaking even. Here, we want to see where our revenue is higher than our cost. That's just extra. That was not part of the question. It just wants to know when you're going to break even. Okay, So what I want you all to do now is I want you to go down to letter C. Okay, try it on your own, and when you are done, check it with me, which is going to actually be just right here this very moment. Okay, so we have a punter kicking a football. Okay, its height in meters. T seconds after the ball is being kicked. So we have somebody kicking a football. Okay, and it's probably going to go up in the air and then back down eventually at some point. Okay, so here is us kicking the football. Here's my x-axis, here's my y-axis, or rather, here's my h of t-axis, and here is my t-axis, right? Here's my height as a function of time, and here's my time. Okay, and then the height of an approaching blocker's hands is modeled by the equation negative 1.43t plus 4.26. Okay, so, oh man, I'm not going to draw the other one until we have a little better idea of what this looks like, okay? So let's go ahead and we're going to type the two equations in. So we have negative 4.9x squared plus 18.24x plus 0.8. Oh, shoot, I just deleted all of that hard work I just put in. Plus 18.24x plus 0.8. And then here, negative 1.43x plus 4.26. Okay. Now, again, we're not looking at we can actually kind of see the curve here, but we are not necessarily looking at the right frame. So again, we know that this graph is going to start at 4 and it's actually going to decrease. And this one starts at 0.8. So I think it's fair to say maybe the y-axis we want to start at 5. And again, I'm not very interested in zeros, although or in negative numbers. So we're just going to have that. I'm going to put it down to negative 1 so I can see the y-axis. But the x maximum, I honestly have no idea. So let's just go with something like 10 seconds. That seems pretty late. So what we're going to do is we are going to, okay. All right, so we need to get, okay, so our graph goes way higher than this. So here it's going to be something like this. Okay. We actually need to take that y value up quite a bit and shorten that x value. So we can go to x is 5. And then this one needs to go up quite a bit. Let's just go ahead and go to like 50. Okay, maybe 25. There we go. Great picture. Okay, so again, you're going to have to do a little bit of wiggle room with that, okay? So where is this person's hands going to cross the ball? Okay, whether they can knock the ball down at all, okay? So it looks like to me the reasonable spot that they can get their hands on the ball is just like right in here. So let's go ahead and second trace, and we're going to look for the intersection. Okay, and on the first curve, I want to get as close to where I believe it's intersecting as humanly possible. It's going to take a lot of time here, which was right about here, give or take a few. Okay, yep, right about there, and I want to guess. Okay, so this here says it's going to intersect at approximately 0.184. Comma 3.996. Just approximately, okay? All right. Okay. So, we want to know, can the blocker knock down the punt? If so, at what time does it happen? The answer to that is yes, because the height of this person's hands ends up after about 0.84 seconds, so not even a whole second after the ball. So they got a really good jump on the snap, and they're hitting it. So can the blocker knock down the punt? The answer to this is yes. And if so, what time after 0.184 seconds. Okay. Okay, let's talk about why, although it is going to intersect down here, right? The graph intersects down here. Why am I not even checking that? The answer, it has no context, right? Having negative height from the field of play isn't realistic. It doesn't have any meaning in the context of our problem. Okay, so I am going to ask one more extra problem on, or extra thing on this particular one, but it has more to do with what we did previously. What if I want to know this question? When would the punt hit the ground if it wasn't blocked? After how much time would it take for the ball to hit the ground? Okay, so what does that mean? I want to know when my height is 0. When would it hit the ground? I'm looking for this spot right here. Okay, which that's an x-intercept. Okay, so let's go ahead and see. We can actually find that on our graph, so we're going to hit second trace. And then this one is a 0. This is when I'm finding the y value to be 0. Okay, and so then, again, I need to get to the left of it. Okay, and so even though I can't necessarily see it great, what we can do is look at the y values. Okay, and again, this is kind of taking forever. Okay, but as I'm looking at the y values, we can see they're decreasing. To be to the left of it means my numbers are positive here, right? So my y value is positive here, and then I hit to the right. I know I'm to the right of it because my y value is negative, and then hit enter again. So after 3.65 or 765, so after 3.765 seconds approximately, right? This is all just an approximation. So it takes about almost 4 seconds, a little less than 4 seconds, for that ball to get up and hit the ground. What if I was asking what's the highest the ball went? Well, what one of these options would I be looking for if I was asking for where the ball is at its highest? Well, I would be looking for its maximum. Okay? And then again, you just have to get to where and you can look at the y values again. You just want to get to the left of what you believe the highest point to be. So as I keep ticking more and more and more, it looks like it's good. My guess is it's in the 17s based on those numbers that we just saw, approximately. Maybe 17.7, something like that. Okay. And just hit enter a bunch of times. Yeah, 17.77. So, and then we know the ball would be at its highest at about 17.77 feet. Meters. Sorry. Okay, and I know that those questions weren't asked in this, but I think it's a good helping hand just to get a little bit of extra thought about parabolas and where the different contexts of the options on our calculator can go from. Okay, just like I did in the previous section, I took a screenshot of the calculator and I gave you a walkthrough of how to do all the important stuff. So if you want to know when two graphs cross each other, I gave a walkthrough. You're going to write each equation. You're going to hit graph, second trace 5, which is your intersection. Hit enter. It's got all the tips that you're going to need along with screenshots of the calculator. Okay, so go ahead and use this to help get yourself going. But at some point you'll have it just memorized. Okay. So that's there to help you out. Otherwise, that will be the it of 3.4, which is systems of nonlinear equations. So hopefully you felt like you accomplished this learning target. And go ahead and get a little bit more practice with this on the homework. And I will see you back for the next section, which is 3.5.